Floor is yours.
Thank you very much for the kind introduction. Good afternoon, ladies and gentlemen. Welcome to my talk. I'm going to provide you some sort of insight about knowledge-based maintenance. I have a challenge that we are in the final session, and the topic is quite complex. So two keywords for you is knowledge-based maintenance and, let's say, sustainability. So let's see how these topics are meeting one the other. So if we are starting, and I would like to start my presentation upon the whole presentation you have seen over the past 2 days with regard to number of approaches. When we are looking at the industrial systems of today, we see that they are tending to become more integrated, data-driven, and complex. If we are looking at these machines provided by, for example, EMCO or HOMAG, we see that from the side of original equipment manufacturer, what matters in the design of this system is to assure the reliability, in fact, and maintainability aspect. And when we come into the machine user field, in the user phase of the machines, we see that availability, uptime matters to ensure the productivity at the end of the day. And these factors are correlating somehow. So both sides, OEMs and machine users, they are sharing the view that they want to gain some sort of benefits from the data to build a kind of an intelligent functions for integrative analysis and modeling of these factors. And in this indicator scheme that we have some sort of a relations theoretically between all these indicators and key performance indicators, what is missing is sustainability. So if we are coming into the context of the problem space that we have with regard to sustainability, we could have started from the triple bottom line of sustainability, looking at the environmental conservation issues, the goal of the 2050 for reducing of the emission and achieving a net zero, then further on the economic enhancement that we need to consider optimizing life cycle costing, and further on the social efficiency, so that reducing the most error-prone sources of the failures, that is human, actually. And on the solution space, when we are really focusing on the maintenance, we see that there are two major approaches. One is that introducing new kind of machines into the shop floors, AI-enhanced machines. So maintenance by design comes into discussion, and we have heard some talk about this topic from the side of the OEMs. And the other side is that maintenance by operation, so extending the remaining useful lifetime of the machine. And when we are just focusing on the first passive research, we see that it has some sort of a contradiction to the topics of sustainability, because we are putting a lot of resources, physical, virtual, and human resources at the service to design and operate these machines in the shop floors. So the research question that comes into discussion for us for over the past, let's say, 7 years is with regard to use of the multi-channel data sources and existing prior knowledge, as well as the human experiences for increasing efficiency in the planning and operating of the maintenance activities. When I talk about maintenance optimization, I refer to the operational, tactical, and also managerial issues that we have, and all are data-driven, and in fact, relating those aspects to the sustainability. So as an impulse, we could say we believe that the maintenance is the key for optimizing the performance, achieving sustainability, and the joint efforts of OEM and machine users are demanded to achieve this goal. So let us continue with this topic of knowledge-based maintenance to make it a little bit more understandable for you. What we mean from knowledge-based maintenance is integrating predictive and prescriptive maintenance. So it is upon and based on the top of actually condition monitoring and the other approaches that we use for the automatic diagnostics. So when we talk about predictive and prescriptive maintenance, there are certain challenges that we need to consider. So first of all, the well-known challenge of proper use of multiple data sources. Then on the top of this is that suboptimal use of multi-structured data. We mainly focus on the sensors, forgetting huge amount of data that we have so-called textual data, for example. And then when we have multi-structured data, we need to deal with the multimodality of the data. So we need to establish some sort of a semantic relations between the information that we are extracting out of the data, either structured or unstructured. And then not forgetting that in the companies when we go, we have multiple strategies for the operating of the machines. Different, contradicting sometimes, reliability sentence and maintenance strategies that we have. And beside of this, we have multidimensionality of the organization in the maintenance, different actors that we have, and in fact, heterogeneous IT landscapes, which is evolving in the companies over the years. So to make it more understandable in the context of global production and manufacturing, we could assume that we have a kind of a CNC machine, an identical one standing in different shop floors all around the world under different operational and environmental conditions. What we get from the OEM, actually, for the object-oriented analysis is a quite rich database that we have, including the failure modes, possible severity of those, causes, risk, and so on. And this could be well used for the machine itself and different subsystems of the machine. So with this, we could do some sort of FMEA analysis, defining the causes and effect, and do some sort of a risk-based analysis for tokenizing of the risk of failure. But when we go to the operation, we have multiple other databases. In each shop floor, we have the failure databases, including all the history of the failures. We have condition and process monitoring. We heard quite a lot about this over the past 2 days. But not forgetting, when we talk about unstructured data, a quite rich database is a textual data. And those kind of data that you get it as a maintenance reports in different qualities, they need to be pre-processed and needs to be quantified, in fact. We need to know what we want to gain out of the textual data when we are analyzing. And another source of the human experiential knowledge as well as the unstructured data is, in fact, cases that we are resolving. And each case consists of a problem and a solution that we are providing. And those solutions are sometimes similar for the certain problems that we have. And we should not start the solving of a problem from scratch. These processes can be also automatized using the similarity learning approaches, case-based learning in that case. And not forgetting that in the production, we have a quite rich database of production plans and production schedules. So if we get all this knowledge in a very ideal world, so that we are getting all the objective and subjective knowledge, we could pre-process this, then we have the sources of knowledge for modeling of our failures and modeling of our indicators, in fact. But this needs to be a structure and represented in a kind of a knowledge representation. There are different ways doing that. I would like to just focus on one of the methods. This is so-called Bayesian network, which helps some sort of a joint probability analysis by considering the causes and the effect, in fact. And with this, we could model certain type of failure depending the object-oriented analysis that we have already talked about it for the machine. And then, as far as we have this network relating different causes to the effect and the joint probability of those, so we could introduce the time series to that and conduct some sort of what-if analysis in different time slices. So with this, we could do some sort of a reasoning and inference out of the network. And imagine that we are modeling one type of a failure for the crack detection of a belt part of the CNC machine. We could consider different modes of the failure and model it like this. And as far as we have the failure and the risk of failure, we could link this to the indicator schemes that we have. Mean time between failure, mean time to repair, so that we are modeling our availability. And as far as we have availability, we can consider the probability for the changes on the maintenance planned activity and unplanned. And with those activities, there are associated costs, so we could calculate the cost of maintenance in that sense and link it to the productivity that we have. So you see that we are starting from a low-level failure modeling in this network up to the high-level indicators that we have for the strategic decision-making. And we could expand it to the other indicators that we have in this scheme. So if we just take one of those CNC machines in one of the shop floors, and looking on the profile of that machine, we know the location, the remaining useful lifetime, we know the age of that, in fact, we know the configuration, the working conditions, and so on, and we get the data from the condition monitoring system. For me, is not anymore the problem whether we have an anomaly or not. For me, the problem is that when I get a signal, how I interpret it in terms of maintenance planning. And maintenance planning, based on the health index, has been introduced for a long time to the literature. But we know that in reality, in the production, this is not linked to the production plans. So that the maintenance teams are coming and in the active time of production stopping the, let's say, production for conducting some sort of, let's say, repair or corrective actions. So this is not a trivial problem when we are considering all the complexities in production plans and maintenance plan, considering all the maintenance logistic and resources. And in fact, when you get the signal, This is the question whether you conduct the activity right away. Is it after the preventive maintenance that you have conducted or before? And how much does it cost for you? So we could say that this kind of a network could help us at least making a kind of an informed decision. In fact, increasing the remaining useful lifetime of our machine, considering the health index that we have for the machine, and the plan for putting loads on the machines, or let's say, optimizing the workload of the machine and maintenance activities at the end of the day. So if you want to bring this into reality, we have thought there are nice approaches, but we need to have a kind of a reference model for this. And we have introduced it in a number of publications, the kind of a so-called prescriptive maintenance model, PRIMA, which consists of 4 modules, actually. Very abstract to say. The first module is the multi-channel data acquisition layer. On the top of this, we have data analytics layer dealing with different type of data, let's say structured and unstructured data. And on the top of this, we have, of course, the communication layer, like any kind of expert system. But this loop won't be completed if you don't have any kind of a semantification layer, linking your prior knowledge that you have in your knowledge bases to your, let's say, new knowledge that you gain, and vice versa, storing and preserving your new knowledge that you gain through every instance of decision-making and prediction, in fact. We are generating some sort of new knowledge and insight. If you are not integrating this into your knowledge base, so you're losing your knowledge in between. So we need to close this loop, actually. And these 4 modules are coming, in fact, into discussion to build a kind of a knowledge-based maintenance approach. And this was a basis for conducting a number of projects over the past years, based on each module or integrating some aspect of these modules together with the industry or with the research partners. I would like to take one of these projects, which we have conducted over the past years with the semiconductor manufacturing, with Infineon in Austria. And we focused in this project on the use of textual data, in fact. And we said that what are the useful information that we could extract out of this textual data, that they have it in the semiconductor for many years, actually. They have a good system for recording of the documentations. And those are, however, are in different quality and in different languages. You know that this is not always a German, and if it is a German, it's with different dialect that we have and different type of formulations. So it's quite difficult to understand the syntax somehow. So we needed to understand the syntax and build up some sort of ontology on the backbone of these to identify the terminology. And then the question was that what can we gain out of analysis of the textual data? So we could quantify this, and as far as we have in the documentation, the timestamp for the reports and so on, we could gain some sort of knowledge. So we decrease the reaction time to the action, to the failures or to the problems that are reported, actually. So you have a sensor data on the machine that reported something, you get an alarm, but you have also the insight of the maintenance engineer that visited actually this machine and could provide some sort of a feedback. These could be linked to each other and will enrich our database and enrich, in fact, the basis for our decision making. So that was very, in a nutshell, very quickly in the afternoon about the knowledge-based maintenance and its impact on the efficiency. But what about the second part of my question? And this is an ongoing research that we do with our PhD candidates, actually, in the research group with regard to sustainability. We are working with the keyword sustainability-driven maintenance. But what does it mean, actually? When we are looking at the sustainability with regard to maintenance, we need to find a kind of a basis for that, to integrate sustainability into the maintenance indicator schema. And one that could be well interpreted by many of the companies is the OEE. So OEE is a benchmark, in fact, to assess the production efficiency and maintenance competitiveness. I'm not jumping into the formulation of OEE, for most of you are well known, but it consists of different losses in availability, in performance, and in quality. And it considers a truly productive manufacturing time. So losses in their schedules and utilizations are not considered with this. So the question that could be extended here is, how can we correlate the OEE losses to the sustainability factors and introduce a new measure that contributes into the efficiency, lean at the same time, and sustainable production? So with this, we can elaborate on each of the losses that we are modeling, in fact. So our knowledge map could be elaborated. We have different sources as a system availability issues, for example, that are contributing to different aspects of our sustainability triple bottom line. So related to the economic factor, related to the human factors when you think about the human error rate, for example, or related to the environmental issues. Those needs to be labeled, first of all. And then we have other type of losses that we have. So, but these are still with regard to the existing OEE and the state of the art. So it's still not contributing to the sustainable production management. What we need is an extended indicator, in fact, so that we are considering the overall sustainable equipment effectiveness on that sense. And in this regard, we need to elaborate on the kind of a new damage or loss model, considering the environmental factors. But you see most of the research that goes on in that sense are focusing on the footprint of the materials. And the databases that you have are mostly focused on the products, like the CIMA-Pro that you have, or the Gabi and so on, not focusing on the processes, in fact. So this needs to be investigated. I leave it open for discussion, in fact. There are, however, other sources beside of the CO2, so we could think about other type of emissions, waste, and so on that we have. And not forgetting that in this context, other management concepts like the retrofit management and so on should be linked to the maintenance management portfolio that we have. And then not forgetting that although the environmental factors are boundary conditions, and we are not allowed to compromise them theoretically against the economic factor, but there are certainly economic factors by the companies, and in fact human factors that needs to be considered and not to be undermined. So in a realistic way of approaching sustainability. And then if we are introducing such kind of a damage model, or at least part of that, then we are able to extend the scope of OEE and assess the competitiveness of our maintenance activities, not only with regard to efficiency, but also with regard to sustainability. And this could be introduced as one extension to our Bayesian network, the dynamic Bayesian network that I have introduced on the former slides. So quickly, to keep with the time, to summarize actually, in our context of research, we have certain challenges still that is shared with most of you. We are talking about the existence of data. I shouldn't talk about it in this community, actually. This is quite well known. But what matters for the knowledge-based maintenance is the correctness and validity of the data, especially when we talk about the sustainability-related data. So, and those databases that we need somehow longitudinal data, those needs to be well validated. And then the correct interpretation matters when we approach a knowledge-based maintenance. And this correct interpretation is not only on the side of the algorithm itself, but also on the side of human. So we need explainable AI to help us to understand the finding and interpret it in the right way, depending on the context and the domain that we are working, and at the same time training and upskilling for the, let's say, workers and engineers that we have at the companies. Not forgetting that this approach will become more complete and more comprehensive if we are considering human experiential knowledge more and more from the process engineers, maintenance engineers, blue and white collars I would call in that sense, and employing other approaches that are very well common in the context of, for example, digital twin, like simulation-based approaches, or what the group of Professor Fink make a lot in that sense is a physics-based or physics-based approaches that could be linked to this as well. But as far as I'm an industrial engineer, I would say those approaches makes only sense for you as an industry people when we are considering and assessing systematically the technical and economic plausibility of this, so we are generating some sort of added value at the end of the day. And with this, I hope that I could encourage you for a further discussion. Thank you very much for your attention.